Hello, welcome back to Learn Physics. In today's topic, we are continuing with our electrostatic potential and capacitance. Okay, so in last class we were studying about the potential energy of a charge and potential energy of a charge if it is placed in an external field of a system of charge also we learned, right? So, and I had given some questions for your homework, so I think it's not a difficult question and all, everything is easy question only. Then also I'll discuss some of the questions in that yesterday's homework. Okay, so one was like what is equipotential surfaces never intersect each other. Why? So usually we know electric flux won't intersect each other, or it will be flux lines. Okay, magnetic flux lines won't intersect each other. Then in that case and all, what will be the answer we will be giving? See, it is a if it is intersecting each other, it will be showing this two directions. Right, so here also same case only, it will be showing at the intersection point, it will be showing two directions, but it is not possible that at one point electric field will be having the more than one direction. So electric field, equipotential surfaces, that equipotential surface lines, equipotential surfaces will never cross each other. Okay, so the next one was here. What is the work done in moving a test charge Q through a distance of 1 centimeter along the equatorial axis of an electric dipole? Okay, in an electric dipole, what is the work done in an electric dipole along the equatorial line? Okay, so here in a dipole, see, if we are considering this is minus q and this is plus q, a point charge over here which is at a distance 1 centimeter in the equatorial line. So it is here just exactly at the equatorial line. So what will be the work done? Work done, to find out the work done, we can Q into potential. For that, what is the potential due to a dipole? 1 by 4 pi epsilon 0 P cos theta divided by R square. Right, so P cos theta, what is the angle between this direction of P and this distance R? So it is perpendicular, so cos 90. What is cos 90? Since cos 90 is 0, V will be equal to 0. So what will be the work done here? Work done will be equal to 0. Clear? So the work done in a potential in a dipole, work done in an equatorial line of the dipole will be equal to 0. Clear? Another question was electric potential at a point O due to a number of point charges equidistant from O is V1 when charges are uniformly distributed, and it is V2 when the charges are non-uniformly distributed. Is V1 equal V2? Justify your answer. So at the point O, okay, and we are considering at equal distances. At equal distances when the potential is considering. Equal distance I am considering, then it will be a circular in manner. Right. So this distance also same, this distance also same, distance also is same. So this is an equipotential surface. Right. Distance is same from the charge. It will be equal potential. Okay, and if this is uniformly distributed at equal distances, Q is over here, Q is over here, Q is over here, this is Q. Okay, so here it is uniformly distributed, right? So here I am considering non-uniformly distributed. See, all the charges are here at this point. Okay, it is not uniformly distributed. Then the potential, what will be the potential in that case? Here it is given as V1, this is given as V2. Whether V1 is equal to V2, that is the question. Right, so but we know V is equal to 1 by 4 pi epsilon 0 Q by R. R is the distance, right? Distance of the charge from the distance of the point from the charge. Okay, so here that r distance is same even if it is uniformly distributed or non-uniformly distributed through the same distance, the charge is same. So here the distances and distance also same. So B will be equal if it is uniformly distributed or it is non-uniformly distributed. Clear? So if it is uniformly distributed or non-uniformly distributed, potential will remain same since it is depending only on the distance. If distance varies, then according to that potential also will be varying. Okay, so these are some of the questions which I gave you in the last class. So I think all the questions, it was easy only, it was not a difficult questions. And so last class we were discussing about the potential energy and we didn't do numerical related to that, so that also we will do today. And next one more is there, potential energy due to a dipole. Okay, so we did the potential due to a dipole, electric field due to a dipole we did, potential due to a dipole we did. Now we are going to do potential energy of a dipole in an external field. Okay, I am considering an external field. There, what will be the potential energy? So next is potential energy of a dipole if it is present in a external field. Okay, I am considering external field E like this. Okay, this is an external field. Direction is this one. Here I am considering a minus q and a plus q, which is having a distance of 2a, which makes an angle theta. Then what will happen? Yes, a torque will be acting on the system since the line of equal and opposite and different lines of action, QE and minus QE and QE. So different lines of action. So it will be having a rotational effect. For that, what we found out already, we found out the torque acting on the dipole. So what is the torque acting on the system? Torque equals P cross E. We already learned that is PE sine theta. Okay, we have torque acting on the system. To find out the potential energy, what we should do? We should do the work done on the system. So how we can find out the work done? Work done in rotational motion will be equal to integral theta 1 to theta 2 d theta. So what is 2 here? Integral theta 1 to theta 2 is PE sine theta d theta. Okay, clear? So here PE is taking it outside. Integral sine theta is minus cos theta. Integral sine theta is minus cos theta, theta 1 to theta 2. While substituting, we will get it as minus PE cos theta 2 minus cos theta 1. So first we are considering the angles. Suppose this P and E are in the same direction. Okay, that is initially both are at same angle. Okay, theta 1 is equal to 0. Then theta 2 is becoming theta. Then how we can find out the work done? Work done will be equal to minus PE cos theta minus PE cos theta 1. Cos 0 is 1. Okay, and suppose if P is like this and E is like this. Okay, both are making an angle 90 degree. That is theta 1 equals 90 degree and theta 2 equals theta. Then how it will be changing? Work done will be equal to minus PE cos theta. Cos 90 is 0. So minus PE cos theta, or we can write it as minus P dot E. Okay, so this is the representation. This is the torque acting on the system. Okay, now we got by this method the potential energy of a dipole. We got it as torque equals P dot E minus P dot E. Okay, now yesterday we learned another method to find out the potential energy. How we found out that one? QB. See, one charge is present, plus Q is present over here. Then an external electric potential also there, V of R. So what will be the work done to bring the plus Q charge in that external field? Q into V. Okay, and next I am bringing another charge, that is minus q. So what is the total potential energy at that? Minus q into V of R2. Okay, then again the energy work done to work between plus q and minus q. Okay, how we can find out? 1 by 4 pi epsilon 0 q1 q2 divided by r square. Okay, using that again we are going to find out the potential energy in this way. Whether we are getting both at the same way or not, we will check. Okay. So again we are going to do in the same manner which we did in the last class. Okay, so plus q one charge is there, minus q another charge. Next we are bringing these two charges, we are going to take into the external electric field. Okay, so here already one charge is there which is having an external field is there. V of r is the potential in that charge. Then what will be the work done to bring plus q charge? Bring plus q charge as q into V of r. Okay, then work done to bring the charge minus q is, what will be this one? Minus q into V of r. Minus q into V of r. Okay, so here we are getting the total. Next is work done on minus q against plus q equal to 1 by 4 pi epsilon 0 q1 q2 divided by r. What is q? Plus q. q2 is minus q. So we will get it as minus 1 by 4 pi epsilon 0 q square by r. Okay, so this is the potential energy over here. Next we are going to find out, see what will be the total work done. So total work done will be equal to, so here work done to bring the charge plus q is q into V of r1. This is work done to bring minus q is not on q. It is having a distance of 2a, right? So this is dipole. So here this is q into V of r2. Now, what is the distance work done on minus q against plus q? 1 by 4 pi epsilon 0 q1 q2 divided by r. q1 is plus q, q2 is minus q. So what is the distance between q and q1 and q2? 2a. So we can write it as 2a here. Total work done will be q into V of r1 minus q into V of r2 plus 1 by 4 pi epsilon 0 into minus q square divided by 2a. So here minus q square divided by 2a. So this equation I can write it as q into V of r1 minus V of r2 minus 1 by 4 pi epsilon 0 q square divided by 2a. So now we are going to find out what is V of r1 minus V of r2. So potential difference in this, so this is the uniform electric field. Here we kept a charge plus q and this is minus q, which is making an angle theta. Now here difference V of r1 minus V of r2. How we can find out? This is difference in potential is equal to integral E dot dl. Isn't it? So E dl cos theta. E dot dl. We can find out that E dot dl. So this is electric field. This is dl. Right? So what is the angle between these two? See, I am taking the component which is in this direction. So dl cos theta. So now it is same, right? So E dl cos theta. Okay, so we already learned about the potential gradient. dV will be equal to E dl. Right, so here E dl cos theta, dV equals E dl cos theta we are getting. So total work done will be equal to Q into E. What is dl here? dl is the distance between these two, that is 2a cos theta minus 1 by 4 pi epsilon 0 q square divided by 2a. What is this q into 2a? That is Pe cos theta. So here V of r1 minus r2, that is V of r2 minus r1. So here V of r2 minus V of r1 is E dl cos theta. R1 minus R2 will be equal to minus ADL cos theta. So it is PE cos theta minus 1 by 4 pi epsilon 0 Q square divided by 2A. So clear? So by integration method when we did, it will be equal to minus P dot E. Here also we are getting minus P dot E minus 1 by 4 pi epsilon 0 Q square by 2A. One more term is coming. Okay, so what is the reason behind that? Because this is due to the work done on minus Q against plus Q. For a given potential, for a given dipole, while we are considering plus Q, minus Q and 2A are not changing. It's a constant. Only theta value will be changing depending on the values. Right. So E is, this Q is constant, A is constant. As the external electric field changes, according to that, theta only is changing. So in the potential energy, different energy while we are finding out, so this constant is insignificant over there. Okay, that is the reason we are finding out this value. Okay, we are considering only minus P dot T. Clear? So while integration method, while we are doing torque, we will get it as torque tau equals P dot T minus P dot E we are getting over there. But by the normal potential energy, while we are finding out, we will get it as 1 by 4 pi minus P dot E minus 1 by 4 pi epsilon 0 Q square by 2A. Okay, so minus P dot T minus 1 by 4 pi epsilon 0 Q square by 2A. In that, minus 1 by 4 pi epsilon 0 Q square by 2A for a given dipole, it will be a constant. Okay, so it is insignificant in this case while we are taking the difference. Okay, understood how we are finding out these values? So V of R2 minus V of R1, it is not dl cos theta. How we are getting that? It is using potential gradient. dV by dV equals E dl, or dV by dl equals E. Okay, don't forget about it. So E dl cos theta. So here it is dl is 2A cos theta. Clear? So here the first question is, an electric dipole of moment 5 into 10 to the power minus 8 coulomb meter is aligned in a uniform electric field of 1.44 into 10 to the power 4 Newton per coulomb. Calculate potential energy of the dipole to hold the dipole at 60 degree with the direction of electric field. So an electric dipole moment is given as 5 into 10 to the power minus 8 coulomb per meter. Electric dipole moment is P, 5 into 10 to the power minus 8 coulomb meter, is aligned in a uniform electric field of 1.44 into 10 to the power 4. So electric field equals 1.44 into 10 to the power 4 Newton per coulomb. Calculate the potential energy of the dipole to hold the dipole at 60 degree with the direction of electric field. So from the electric field, we need to keep the dipole at 60 degree. Okay, so it is 0. Initially it was 0. Now it is becoming 60 degree. So theta 1 is 0 and theta 2 is 60 degree it is becoming. So how we can find out the value of this torque acting on the system? With calculate the, not torque, potential energy. Potential energy, how we can find out? That is PE cos theta minus cos theta 2 minus cos theta 1. Okay. Potential energy equals minus PE cos theta 2 minus cos theta 1. Okay, potential energy, I'll write it as potential energy only. Potential energy equals minus PE cos theta 2 minus cos theta 1. So P is given as, what is P? 5 into 10 to the power minus 8. E is given as 1.44 into 10 to the power 4. That is cos theta is theta 2. Now it is becoming 60 degree and initially it was 0, cos 0. So we will get it as minus 5 into 1.44 into 10 to the power minus 4 cos 60 1 by 2 minus cos 0 1. So we will get the answer while finding out. Okay. So otherwise I will do 5 into 0.72 into 10 to the power minus 4. So 3.6 into 10 to the power minus 4. What is the unit? Joule. Potential energy, what is the unit? How we can represent the potential energy? Potential energy we can represent it in joule, and electron volt also we can represent. Okay, 1 electron volt equals 1.6 into 10 to the power minus 19 joule. Okay, and giga electron volt, mega electron volt, tera electron volt, everything is there. So giga means it has 10 to the power 9, and mega means 10 to the power 6, tera means 10 to the power 12 electron volts. Okay, this unit also important. So to convert the joule into electron volt and all, you should convert like this. 1 joule equals 1 by 1.6 into 10 to the power minus 19 joule. If you want to convert joule into electron volt, you should divide. Okay, and then see 1 electron volt equals this much of joule. So you should convert a joule to electron volt, means you can divide it with the 1.6 into 10 to the power minus 19. Then giga, mega, tera. This you should keep in mind. Okay. So another one is, this is a previous year question, that is 3 point charges plus Q plus 2Q and minus 3Q are placed at the vertices of an equilateral triangle ABC of side L. If these charges are displaced to the midpoints A1, B1, C1 respectively, find the amount of work done in shifting the charges to their new position. So here the diagram is given like this is A and this is B and this is C. Here Q, this is 2Q and this is minus 3Q. We need to bring A to A1, B to B1 and C to C1. What should be the work done? How we can find out this work done? So initially what is the potential, what is the potential energy? Now at A1, B1, C1, what is the potential energy? Difference in potential energy will give you the work done. So initially when at positions A, B and C, A, B and C. Okay, so these three positions, what is the potential energy? 1 by 4 pi epsilon 0 Q1 Q2 by R. This is the equation, right? So using this equation we can find out like, so B equals total potential energy between A and B and plus potential energy between B and C plus potential energy between A and C. Okay, so what is the potential energy between A and B? 1 by 4 pi epsilon 0 Q 2Q divided by, what is the distance? L, plus 1 by 4 pi epsilon 0 between B and C, 2Q and minus 3Q divided by L, plus 1 by 4 pi epsilon 0 minus 3Q and Q divided by L. So here everywhere Q square by 4 pi epsilon 0 is common, L is common, and here 2 minus 6 minus 3. So we will get it as, see, minus 7 Q square by 4 pi epsilon 0 L. Okay, same way if we are finding out for our this position A1, B1, C1, the charge everything is same, only difference is instead of L it will become L by 2. This distance is L by 2 and this distance is L by 2 and this distance also is L by 2. Okay, so what is the distance between, so this distance how we can find out? Same way, L by 2. Okay, so here we can find out V is equal to 1 by 4 pi epsilon 0 Q divided by L by 2, L by 2, L by 2. So here we will get it as, so instead of L by 2 will be coming minus 14 Q square divided by 4 pi epsilon 0 L. So this is the final potential. This is the initial potential. So what is the potential energy difference? So work done will be equal to Vf minus Vi. Vf is, see, minus 14 Q square divided by 4 pi epsilon 0 L minus 7 Q square divided by 4 pi epsilon 0 L. So Q square divided by 4 pi epsilon 0 L, that is common. into, here it is minus 14, minus minus is plus 7. So final answer is minus 7 q square divided by 4 pi epsilon 0 L. Okay, clear? This is how we will be finding out the potential of an, and see how we can find out the potential. So this is how we are finding out the potential energy. So these and all not potential, potential energy. Okay, now don't write it as V, this is U. Okay, so U potential is, we are representing, potential means what is the formula? 1 by 4 pi epsilon 0 Q by R. So this is Q1 Q2 divided by R. Potential energy only we are finding out. Difference in work done will be, difference in potential energy will be the work done of the system. Okay, clear? So this is how we are finding out the final equation. So I think it is clear for you, and if you like the channel, please don't forget to subscribe. Thank you for watching. Bye.